August 1941, Detroit, Michigan. Inside the Packard Motor Car Company's East Grand Boulevard plant, a low roar filled the air. Two Rolls-Royce Merlin engines shuddered to life on the test stands. But something was unmistakably different. These weren't engines shipped across the Atlantic. They were American-made marvels, forged from British blueprints, yet transformed by Packard's engineers into something entirely new. The crowd watching that day had no clue. They weren't just witnessing engines running. They were seeing the birth of an engineering revolution. Buried deep inside those Merlins was a secret that would ripple across World War II. Bearings had been redesigned, tolerances tightened, and even every thread on every bolt painstakingly replicated from Britain's intricate Whitworth system. Detroit had taken what was once a hand-fitted luxury engine and turned it into America's most producible powerhouse, defying every Rolls-Royce convention in the process. This is the untold story of how Packard engineers solved an impossible puzzle, not by winning battles in the air, but by conquering something far trickier, converting 14,000 precision parts from Britain's imperial measurements into American mass production without losing a single horsepower. Dear friends, if this video has reached you, it's not by chance. Right now, click the subscribe button and the notification bell. Write a number from 1 to 5 in the comments. I will personally respond to the first 50 comments and make sure to watch the video until the end. By early 1942, the United States Army Air Forces faced a dilemma. They had a fighter they admired and a fighter they couldn't use. The P-51 Mustang, powered by the Allison V1710 engine, dazzled at low altitude. Agile, fast, lethal below 15,000 feet. But climb above that, and it struggled. The airframe wasn't the problem. North American aviation had crafted a masterpiece. The enemy was physics. The Allison's single-stage supercharger couldn't compress enough air at high altitude. At 25,000 feet, the cruising height of German fighters, the Mustang's power dwindled. By 30,000 feet, it was almost defenseless. And the cruel irony? American bomber crews desperately needed escort fighters at precisely these altitudes. B-17 flying fortresses soared between 25,000 and 30,000 feet, deep over Germany, and without capable escorts, they were sitting ducks. In August 1943, during the infamous raid on Schweinfurt, 60 bombers were destroyed in a single mission. The Luftwaffe knew the Mustang's weakness and exploited it ruthlessly. Climb above it and wait. The Army Air Forces didn't need a new fighter. They needed a new heart for the one they already had. 3,000 miles away, in Derby, England, Rolls-Royce Limited held the answer. Their Merlin engine powered Spitfires and Hurricanes to altitudes the Allison could only dream of. The secret? A two-stage, two-speed supercharger engineered by Stanley Hooker, capable of maintaining sea-level pressure all the way to 30,000 feet. But the Merlin wasn't just an engine. It was philosophy-made metal, each one hand-built. 14,000 individual parts, fitted by craftsmen who could make the impossible happen. If a connecting rod didn't match the crankshaft, they filed it. If bearing clearances varied, each was adjusted by hand. Every fastener conformed to Britain's Whitworth thread system. 55-degree angles, radiused corners, each one unique. Supercharger tolerances measured 1 inches, the width of a human hair divided by 4. Cylinder heads were mated to blocks individually. Supercharger impellers balanced by hand. This was not production. It was art. But war waits for no artisan. By September 1940, the Battle of Britain raged overhead, and Rolls-Royce's shadow factories in Crewe, Manchester, and Glasgow churned relentlessly, producing roughly 200 engines per week when 2,000 were needed. Britain looked across the Atlantic wondering, could America help? They had no idea they were about to challenge Detroit to perform an engineering miracle, turn precision craftsmanship into mass production without losing a single dimension, a single horsepower, or a century of engineering tradition. The real test wasn't building engines. It was translating an entire industrial philosophy into the language of American manufacturing. When Rolls-Royce engineers arrived in Detroit in September 1940, they brought crates of complete Merlin engines, hundreds of blueprints, and unshakable faith in their methods. The licensing agreement was $130 million astronomical in 1940. Packard Motor Car Company wasn't the obvious choice. They built luxury automobiles, not aircraft engines. But they had something Rolls-Royce didn't: American industrial ingenuity. The moment Packard engineers examined the blueprints, they realized the enormity of the challenge. 14,000 problems, in fact. First, the measurement systems were incompatible. Britain's imperial system wasn't America's, and tolerances expressed in thousandths of an inch needed interpretation, not simple conversion, but understanding the intent behind every specification. Second, the British Whitworth thread system. Every bolt, every nut, every threaded connection used a 55-degree angle with radiused roots. American unified threads were 60 degrees, flat-rooted, and entirely incompatible. Packard would have to manufacture every fastener themselves. Third, and perhaps the most daunting British tolerances, were designed for hand-fitting. Merlin parts expected human craftsmen to adjust, filing and tweaking as they assembled. Detroit didn't do that. American mass production demanded perfect interchangeability. Any part had to fit any engine, no exceptions, no adjustments, no craftsman magic. The British engineers were polite but skeptical. Could American factories truly honor Rolls-Royce standards? Packard's lead engineer, Jesse G. Vincent, gave them a shocking answer. "Your tolerances are too loose for us." Silence filled the room. What happened next became legend. Packard didn't just copy the Merlin, they reinvented its production, preserving its essence while making it suitable for assembly lines. Over 11 months, engineers produced 6,000 new technical drawings, not to correct the British designs, but to translate them into American mass production. Every dimension, every tolerance, every process reimagined. And the genius, the magic, was in the details. Imagine standing in a dimly lit Detroit factory in 1941, surrounded by the hum of machinery and the scent of metal. Every component, every bolt, every bearing mattered. Take the crankshaft bearings, for example. Rolls-Royce had long relied on a copper-lead alloy that demanded painstaking break-in and constant inspection. But Packard's metallurgists, drawing from the cutting-edge research of American aircraft engines, dared to try something new: a silver-lead alloy plated with indium. The silver could carry heavier loads, while the indium created a microscopically flawless surface that reduced friction and made the break-in smoother. British engineers scoffed at first. This wasn't the Rolls-Royce specification. Yet when testing revealed that Packard's bearings lasted longer and ran cooler, even Rolls-Royce quietly embraced the American innovation. Then there was the thread problem, a seemingly insurmountable obstacle. Packard couldn't simply switch to American thread standards without rendering engines incompatible with British aircraft and spare parts. So they performed an engineering feat almost unheard of. They built entirely new tooling to produce British standard Whitworth threads to American precision. Every tap, die, and thread cutting tool was custom-made. They imported specialized thread measuring equipment from Britain and trained machinists in systems few Americans had ever touched. BSW for coarse threads, BSF for precision joints, BA for delicate instrument fasteners. The result? Packard built Merlins used the same threads as Rolls-Royce engines, allowing parts to swap seamlessly between Detroit and Derby. And here's the kicker: Packard's threads were manufactured to even tighter tolerances than the originals, eliminating the need for hand fitting. Perfect interchangeability every time. Now, picture the supercharger, the beating heart of the Merlin's high-altitude power. This two-stage, two-speed marvel used dual impellers on the same shaft, rotating through complex gear trains. Low-speed mode ran at a ratio of 6.391.1. High speed, activated by a hydraulic clutch, jumped to 8.095.1. At speeds exceeding 30,000 RPM, the slightest imbalance could shred the engine. Rolls-Royce relied on master craftsmen to balance them by hand. Packard, however, pioneered precision casting and machining techniques so accurate that the impellers needed almost no manual adjustment. They even developed equipment to measure dynamic balance while spinning. The result was production that was not only faster, but remarkably consistent. Then came the challenge of cooling. Compressing air generates intense heat up to 205 degrees Celsius. To prevent detonation, the Merlin used a complex intercooler system with cast passages inside the supercharger and an additional core between the outlet and the intake manifold. 36 gallons per minute of ethylene glycol, pumped by a centrifugal system, whisked away the heat. Packard redesigned the coolant passages for smoother flow and simpler production without compromising performance. Every system, every component, was scrutinized, reimagined, and optimized for manufacturing efficiency while preserving engineering excellence. By August 1941, exactly 11 months after signing the agreement, the first Packard P-51, their version of the Merlin DAX-X, roared to life on a test stand in Detroit. Winston Churchill reportedly wept upon hearing the news. Britain would receive the engines they desperately needed. But building one engine was one thing, producing 55,000 doors was another. Packard transformed their factory into a cathedral of precision. Each station on the V1650 line was dedicated to a specific operation: crankshaft machining, block face milling, cylinder head finishing. American mass production philosophy demanded absolute repeatability. If a crankshaft journal was supposed to measure 2.2495 inches, it was 2.2495 every single time. No hand fitting, no improvisation. Skilled apprentices weren't required. Well-trained workers and excellent machinery were enough. Production soared. By 1943, Packard was building engines faster than North American aviation could supply airframes. At its peak, the Detroit plant completed roughly 400 engines per week, twice Rolls-Royce's entire British output. The V1653, based on the advanced Merlin 63, pushed the P-51 Mustang to unprecedented heights, sustaining over 1,200 horsepower at 40,000 feet, where the Allison engine gasped and wheezed. The V1657 powered the legendary P-51D with its bubble canopy, delivering 1,315 horsepower at sea level and speeds of 437 miles per hour, while remaining lethal at altitudes up to 40,000 feet. These engines escorted bombers from England to Berlin and back, and the Luftwaffe soon feared the distinctive roar of the Merlin high above. By the end of the war in 1945, Packard had produced 55,923 Merlin engines, more than all Rolls-Royce factories in Britain combined. The Packard Merlin wasn't just an engine. It was a triumph of ingenuity, precision, and transatlantic collaboration. It stands as one of the most remarkable achievements in engineering history. What the Packard Merlin proved is profound. Precision and mass production are not enemies. They are partners if you truly understand the principles behind them. Rolls-Royce created extraordinary engines through craftsmanship and human skill. Packard achieved the same excellence through systems, processes, and repeatable precision. Both approaches worked, but only one could meet the relentless demands of total war. The techniques Packard pioneered, precision casting, statistical process control, and custom tooling to guarantee uniform quality, didn't vanish when the war ended. They became the foundation of modern aerospace manufacturing. When you step onto a Boeing or Airbus jet today, the engines powering that aircraft are built using descendants of the very principles Packard perfected in 1941. Even the innovations in bearings had a lasting impact. The silver-lead indium bearings Packard designed for the Merlin, with their exceptional load-carrying capacity and friction reduction, became a standard for high-performance engines in the post-war automotive industry. And the story of thread compatibility? It resonates today in international standards, like ISO threads. Engineers learned during World War II that mismatched fasteners could cripple supply chains, a lesson that shaped global manufacturing protocols for decades. But the most enduring legacy isn't technical, it's philosophical. Packard showed that you can honor tradition while embracing innovation. They didn't discard Rolls-Royce's wisdom, they translated it into a different industrial language. They maintained British thread specifications not because they were forced to, but because engineering integrity demanded it. That respect for interoperability, standardization, and systems that work together still guides modern manufacturing on a global scale. Some of those Packard Merlins still roar today. The Canadian Warplane Heritage Museum in Hamilton, Ontario, flies a Lancaster bomber powered by 4 original Packard engines. At the Reno Air Races, unlimited class P-51 Mustangs with modified Packard Merlins crank out over 300 horsepower, nearly 3 times their original rating. These engines, forged more than 80 years ago, still perform, still inspire, and still demonstrate what American engineering could achieve when necessity demanded the impossible. The P-51 Mustang earned its place as perhaps the finest fighter of World War II, but its secret wasn't just the airframe or the skill of the pilots. It was an engine, born in Derby, England, and perfected in Detroit, Michigan. The Packard Merlin story isn't a tale of one nation's engineering triumph over another's. It's a story of complementary strengths. British ingenuity designed a revolutionary engine. American manufacturing genius made it available in the quantities required by a world at war. 14,000 parts, 6,000 new drawings, 11 months of relentless engineering effort. The result changed the course of history. Next time you see a P-51 Mustang at an air show, lean in and listen for that unmistakable howl of the Merlin. That sound is more than nostalgia. It's a symphony of 2 engineering philosophies in perfect harmony. British innovation, American production. Together, achieving what neither could have accomplished alone. And if you think that's impressive, there's more. In our next story, we'll explore an invisible victor of the war, how American engineers, without ever seeing the Japanese purple code machine, built a mechanical computer from scratch to break it. These are the stories history class often overlooks, not about who won battles, but about how ingenious minds solved impossible problems. And sometimes, the engineering triumph is even more remarkable than the battlefield victory itself.